So now that we've talked about the quantum numbers and we've looked at the angular part of the wave function and started talking about the radial part, what do the actual solutions look like? And so the solutions involve the Laguerre polynomials, yet another dead French mathematician that helped us out with solving our differential equations. And so I'll just write out the form of the wave functions. So the radial part of the wave function depends on n and L. So we write it with the subscript n and L as a function of r. And we get, yet again, big normalization constant. So we get negative n minus L minus 1 factorial divided by 2n times n plus L factorial raised to the third square root of all that times 2 over n a naught raised to the L plus 3 halves. All right, so all that is normalization. And then we have r raised to the L power. So now we actually get the part that depends on our variables. E to the minus r over n a naught. And then the Laguerre polynomials. The associated Laguerre polynomials are written with this terminology L, n plus 1, 2L plus 1 as a function of 2r over n a naught. And what these polynomials look like, you can look at table 6.4 in your textbook to see what these look like. All right, so mostly constants and then a polynomial multiplied by an exponential. So overall, our total wave function depends on these three quantum numbers, n, L, and m. It's a function of three variables, r, theta, and phi. And we have this radial part that we've just written here, and the spherical harmonics. And that is our overall hydrogen atom wave functions. Now, what do these wave functions look like if we put all of this together and we look at specific n, L, and m values? Let me just tab over to this Chrome window. So these are some of the first few hydrogen atom wave functions. So if we combine a bunch of constants, so we have up here, what the value of a naught is, which we've been using in our other equations. These are the wave functions. So this is n, L, and m. So 1, 0, 0, that's what we would call 1s orbital. You see there's no angular dependence, so there's no terms with theta or phi in them. Same thing for 2, 0, 0. Anything that has L equals 0 doesn't have any theta or phi dependence in it. But if we get to 2, 1, 0, we see we have a cosine theta in here, as well as this exponential term. And as we go down, as we have m equal plus or minus 1, we also get this imaginary exponential in here as a function of phi. And we see, right, these mathematical functions get more and more complicated, and we have different different normalization factors here out in front that get looking wackier, right? But this all just follows the formulas that these are all solutions that we can get to the Schrodinger equation. And so in the next video, it's nice having these formulas, but what do they actually look like? And so in the next video, we'll look at some visualizations of the hydrogen atom orbitals.